Hi, welcome to the lesson on the valence shell electron pair repulsion theory, which sounds a lot scarier than it is, I promise. All right, the basis of this entire theory is just on electrons, valence shell electrons to be exact, and we are specifically talking about how pairs of electrons will repel each other. All right, let's keep it simple. So, question of the day, what happens when electrons get close to each other? I'm sure you know, they repel. That's the entire concept here. So when we look at Lewis structures, we know that a 2D picture of a molecule does not indicate the way a molecule would look in 3D. So if you took a picture of yourself, your photograph would be flat, but we know that that's not really what you look like in real life. You ever take a picture of yourself and you don't like it? That's probably because one is 2D and you exist in 3 dimensions. That's kind of why they're different. So the idea here is that a Lewis structure, that's a picture of a water molecule, right? It's 2D, it's flat. It has a height and it has a width in this case. We are not going to be able to see what an actual water molecule looks like because it's not flat living in 2 dimensions, but instead it is a real life structure living in 3 dimensions with a height, a width, and a depth. So this right here shows what a water molecule kind of would look like based on all of the properties that we know about it. Things that you'll learn in Unit 5 on intermolecular forces. But based on the properties of water, we have extrapolated that this is what the shape should look like. So the real life 3D shape of a molecule is going to be based on the number of electrons that are bonded and are not bonded. And we know that those always come in pairs, right? So we are going to specifically talk about bonded pairs and non-bonded pairs on the central atom in a Lewis structure. So in water, oxygen would be the central atom. You have oxygen there. It has 2 lone pairs and then 2 bonded pairs, which bond to the hydrogen. Okay, so that's the difference between a bonded and a non-bonded pair. You may often hear the non-bonded pairs referred to as lone pairs. It just means that it's a pair of electrons that belongs to only one atom. It's not shared between 2 atoms. The first shape that we have is linear. It's the most simple of all of the shapes. First up, we have beryllium chloride, which is BeCl2. Beryllium comes in with 2 valence electrons of its own, and then it's going to share 1 with each chlorine to get a total of 4 valence electrons. This may not be a shape that your teacher is interested in you learning, simply because beryllium is what we would call an octet violator. Beryllium is not interested in having a full valence of 8 electrons, simply because beryllium is too small for that. So even though the beryllium chloride may look something like this, with a beryllium in the center and then the chlorines, it would spin in space, kind of like this. That's what the beryllium would look like. So that one you may or may not be responsible for learning, but I bet the carbon dioxide your teacher does want you to know is linear. So here you have the carbon in the middle bonded to 2 oxygens. And this may look like it's a single bond, but as the molecule turns in space, you can see that it's a double bond. The oxygen and the carbon are sharing 2 electrons here and 2 electrons here, a total of 4, giving you the double bond. Now, notice how this structure drawn right here is different from this structure here. It's just a little bit different. There's far more details as to why one of the pairs goes this way and one of them goes this way. And that's really just because a double bond is very crowded. You got 4 electrons in there and they don't really like to hang out with each other. So this is what the carbon dioxide would look like, and in the real world, most of the time, you'll find this as a gas, so it'll be moving around quite a bit, and this is why the Lewis structure is not the best way to represent real-life molecules. So anytime we have a molecule that has 4 bonded pairs, in this case they're coming 2 and 2, and 0 non-bonded pairs, we're talking specifically about the carbon here. Carbon has no non-bonded pairs on it. It has 2, 4, 6, 8 valence electrons. That indicates that we would have a linear shape. So you can draw a Lewis structure to find the number of bonded and non-bonded pairs, and just with a little bit of memorization, know that your shape will come out linear. Here we have boron trifluoride, which again is going to be an octet violator. And this is because boron, again, is an element that's too small for a full octet. So again, confer with your teacher to know if this is something that they would like you to learn. It's going to wind up looking something like this. And this is an entirely different model kit because this model kit does not really align with the trigonal planar because it is a very uncommon shape. So you'll have your central atom. In this case, that's going to be the boron, the big blue one. And then it's going to bond to 3 fluorines. And you can see that if you connected the dots between these fluorines, you would get a flat triangle. It's entirely flat. So it's kind of rolling through space as a flat triangle. Now, the bond angle between any 2 fluorines is going to be 120 degrees. And this specifically is because it is the way to get the fluorines and their big cloud of valence electrons as far away from each other as possible. That's the entire concept behind valence shell electron pair repulsion theory, VSEPR theory. The idea is to get the valence electrons as far away from each other as possible because we know they're repelling. If you look back to the linear, obviously it makes the most sense to get the oxygen as far away from that other oxygen. Around oxygen, once it's bonded, it has 8 valence electrons, and it doesn't want to be anywhere near this other oxygen with 8 valence electrons. So it comes out 180 degrees between the 2 oxygens. This one's pretty intuitive. When you get to the trigonal planar, if they were in any other arrangement, they would be closer to each other. Okay, so the scientists haven't actually seen a picture of boron trifluoride, but what we have done is a bunch of math to figure out that this is the perfect angle to get those fluorines as far away from each other as possible. Tetrahedral is the next shape, and on that central atom, you'll find 4 bonded pairs and 0 lone or non-bonded pairs. And you can learn that from the Lewis structure, but when you draw the Lewis structure, right, we would typically draw methane like a plus sign. That is not what it looks like in real life. In real life, it kind of looks like a tripod with this one sticking up. We would also say that these atoms are in the same plane. So you can kind of see it here. We have one coming out at you. We have one going backwards. And then this one, the center, and this one coming out, they're in the same plane, which means that they lay flat with respect to each other. They all lay flat to each other. This works a lot better if you have a model kit yourself. So these all lay flat to each other. They're in the same plane. And then these 2 are also in the same plane, but it kind of depends on their arrangement. So these 3 on the bottom spread out like the legs of a tripod, and then this one goes straight up. We call that shape tetrahedral, and the angle between any 2 hydrogens on this methane are 109.5. And that in the 360 degrees that we're working with on this carbon gets those hydrogens as far away from each other as possible. So when methane is rolling through space, mostly a gas, it is going to spin around like this, not like you would draw it flat on a paper for a Lewis structure. Next up is Trigonal Pyramidal, and it's kind of the same thing as tetrahedral, except I have popped off this hydrogen and replaced it with a lone pair. So in this case, we have 3 bonded pairs and 1 lone pair, which is this purple bunny ear. And this would be ammonia, NH3. Here's your nitrogen and your 3 hydrogens around the bottom. And if we ignore the lone pair, the atoms here are going to kind of build a triangle, if we looked at it this way, with this nitrogen being the tippy top of a pyramid. So if you think about it, this is a triangle-based pyramid, which is how we got the name Trigonal Pyramidal. The bond angle between any of the hydrogens, so hydrogen, nitrogen, hydrogen, making that bond, is going to come out to 107 degrees. Now, the reason that these hydrogens are a touch closer than they were in the tetrahedral is because these lone or non-bonded electrons have a little bit more leeway to move around because they're not locked into a bond. So they are able to squeeze those hydrogens together and take up a little bit more space on their own. So that's why the angle between the hydrogens is a little bit tighter than it is in the tetrahedral shape. If there are two bonded pairs and two non-bonded pairs, like there is in water, you wind up with the shape that we call bent. And that is because if you ignore the lone pairs, you have kind of a bent shape. Two bonded pairs right here. They are in the same plane, making an angle of 104.5 between them because water has, or rather the oxygen has two lone pairs that'll squeeze these hydrogens even a little bit closer together than they could in trigonal pyramidal or in tetrahedral. So the reason that these three shapes are often compared is because I call them electron spots. There's 4 electron spots in total. In a bent, 2 of them are bonded and 2 of them are non-bonded. In trigonal pyramidal, 3 are bonded and 1 is non-bonded, but they total 4 bonding spots, right? And then here we have 4 and 0, 4 bonding spots. So these 3 are often related to each other, and you'll see a lot of questions about that bond angle being squished together by the lone pairs. Water has 2 lone pairs, so it is able to squeeze the hydrogens even closer together than you could in that trigonal pyramidal. So when we were drawing Lewis structures, I gave you the clue to draw water kind of at like a right angle for your Lewis structure. Technically, a water molecule drawn straight across as a Lewis structure is correct because a Lewis structure doesn't show you anything about real life shape. It only shows you what's bonded and what's not bonded. So I told you to do that so that you would get the correct answer later on when we talk about molecules being polar or nonpolar. But the idea here is that water is very lopsided. We have this area on water that's very negative with all of those lone pairs, the electrons floating around up there. And then here we have almost a right angle, 104.5, not that far off. And this later on is going to help you with molecule polarity. So if you haven't started, start drawing your water Lewis structures kind of in like a 7 shape because it's going to give you a better picture of what water looks like in real life. So more of what I was saying here is that the lone pair takes up a little bit more space than a bonded pair because they're free to move around. And we often talk about tetrahedral, trigonal pyramidal, and bent being evidence of this. We have 4 spots for electrons on that central atom, 4 and 0 in tetrahedral, 3 and 1 in trigonal pyramidal, and 2 and 2 in bent. So as we get more lone pairs, those hydrogens, at least in this case, all of the molecules we spoke about were hydrogen, but they could be any atom. They get squeezed together closer and closer, which is going to shrink the bond angle. Now, this is some more octet violators. Here we have a molecule of PCl5. And in this case, the phosphorus has 10 electrons because it has 5 bonds in total, 5 bonded pairs and 0 lone pairs. There are 2 bond angles on a trigonal bipyramidal. And you can kind of see it a little bit better in my model here. We have axial atoms, which go straight up and down. Think of like the planet Earth, right? Like this is the North Pole and this is the South Pole. Those would be the axial atoms. And then the green ones that spin around in the middle, those are equatorial or equatorial, like the equator of the Earth, right? So the bond angle between the equatorials is 120. It's kind of like trigonal planar, but you have a lone pair coming out at you, and I have a lone pair coming back at me. So here, this bond angle is going to be 120 between any of the equatorial atoms. And then from the axial down to any of the equatorials will be an even 90 degrees. Okay, so this has 2 bond angles. This in total gets those electrons as far away from each other as possible because around each of these chlorines is going to be a big electron cloud, right? And this has 5 chlorines, so this is big. If we look at it, we call it trigonal bipyramidal. And that is because we have the equatorials making a triangle. I'm going to point it at you this way. You can see the triangle here. And if we spin it back and we consider that triangle, we have a pyramid pointing up and we have a pyramid pointing down. So we would call this trigonal bipyramidal because it's a triangle base and it makes two pyramids, bipyramidal. Octahedral is kind of similar. Here we have 6 bonded pairs and no lone pairs because we have phosphorus again. Octet violator here, it has 12 electrons. It has no lone pairs on that phosphorus. The equatorials are here in the center, and the angle between any of them is 90 degrees, which you can see if I point it at you, right? The angle between any of the equatorial, the green ones, that's all 90. And then between the axial and any of the equatorials is also 90. So they are the same. Perfect 90-degree bond angle. Our equatorials are making a flat square, which you can see if I point it at you perfectly. We got a flat square, and then the axial atoms go up and down. And we could call this square bipyramidal, but it does actually make the shape an octahedron because there's 8 faces between all of these atoms. If you just take any of the 3 atoms, they'll make triangle faces. You would have 8 triangle faces. So that's why this is called octahedral. I know it's confusing because it's 6 bonded pairs and it's octahedral. If you Google the shape of an octahedron, it would maybe click a little bit better if you're not seeing it. Okay, so that one is octahedral. And then if we take that octahedral and we adjust it a little bit, in this case, we're going to pop off one of the equatorials and we're going to put on a lone pair because we have 5 bonding pairs and 1 non-bonded or lone pair. And this one looks just like this. So we have the lone pair bunny ear on the bottom and we still have the 5 bonded pairs. And in this case, all of our angles are still the same. We're still 90, 90, 90. This lone pair can't really squeeze these guys any closer together. So here, again, we have the square. Let me get it. There's a square. Between all those equatorials, we got the square. And this would be the tippy top of the pyramid. So we have a square base to our pyramid, just like the ones in Egypt. And if you were to connect all of these and turn it into a polyhedron, I guess you would call it, you would make a square pyramid. As this moves through space, obviously this lone pair is going to move around. So it could also be done this way, but this is going to show you the square pyramid best. Square planar does not happen very often. You would have 4 bonded pairs. They're all equatorial. And then you would have 2 lone pairs. And because they're really big and don't like to be near each other, they're both going to go axial, meaning they're going to be as far away from each other as possible. The remaining atoms are going to make a flat square. So that's why it's called square planar. The bond angle between any of these is still 90 because you really can't squeeze these any closer together. This one's very rare. You see here the formula is xenon tetrafluoride. Xenon does not really like to bond because it's a noble gas. So this one is something that you have to really force to happen. You know xenon doesn't like to bond. If you look back to trigonal bipyramidal, seesaw is kind of the cousin to trigonal bipyramidal. All we have done is taken off one of the equatorials and replaced it with a lone pair. And here on the central atom, we have 4 bonded pairs and 1 lone pair. The angles are 154, which is going to be here, and 101.6 between these. This is not super accurate, this one in particular. So what happens is if this were rested on those equatorials, the others would be able to seesaw. If you can build this, you will see it far better than me just playing with it. But you see how it's resting on my hand, the green ones? And then the orange ones can kind of seesaw back and forth. That's why it's called the seesaw shape. This, again, is another one that you should probably confer with your teacher if they want you to know it. Because it's, again, not super common. Now, if we were to pop off one of these and again replace it with a lone pair, then you get the T shape. So here we kind of have right there, this would be the 185, and this is the 87.5. And if we look at all of the atoms together, they make a T shape. We got two lone pairs on the top. So this one is showing like this. This one's pointing forwards, and this one back here is pointing backwards. Get a model kit. Play with them yourself because you'll see it best if you do it yourself. All right, those are typical shapes that you would learn with the VSEPR theory. The important thing to remember is that the Lewis structures will tell you the number of bonding and non-bonding pairs, but what you draw on paper is not reflective of what happens in real life. And that's the basis of the VSEPR theory. That's it. Some teachers will have you memorize the shapes. If that is true, I would confer with your teacher on which ones they expect you to know and memorize. For me and my students, it is not T-shape, not seesaw, not square planar, not even square pyramid, but everything from the start of the lesson to octahedral would be the ones I would expect my students to know. So confer with your teacher because different teachers, depending on what level of chemistry you're doing, will have you learn different shapes. And then a lot of it comes down to just identifying how many pairs are on the central atom are bonding and how many of them are not bonding and are hanging out like lone pairs, which we see here in water, 2 lone pairs, ammonia, 1 lone pair, and methane, no lone pairs. That's going to become very, very, very important in the next unit called intermolecular forces because we know that those lone pairs don't like to hang out with each other. We know this because they're all negative. Sorry, I'm trying to find here we go. So when we have multiple water molecules hanging out with each other, let's check that out. These electrons on this water molecule don't want to be near the lone pairs on other water molecules. They don't. That's because these are negative and the ones on the other water molecule are also negative. So it's going to become a big part of intermolecular forces, which we'll learn in the next lesson. All right, that's it. Make sure to comment any questions you have below. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.